Let's now move on to special purpose gates, namely the XOR gate and the XNOR gate. These are widely used in specialized applications such as arithmetic circuits for addition and subtraction, that is, half adder, full adder, half subtractor, and full subtractor. Also, these gates are used for data encryption and error detection systems. The exclusive OR gate or the XOR gate. This is the logic symbol of the XOR gate with two inputs A and B. The output is given by Y is equal to A XOR B. See the truth table. The output is a high or 1 when the inputs are different. Therefore, the XOR gate is also known as the anti-coincidence gate or inequality detector. When the inputs are same, the output is a low or 0. That is, here when both A and B are 0 or when both A and B are 1, the outputs are 0. The name exclusive OR is derived from the fact that its output is a 1 only when, that is, exclusively when one of its input is a 1. That is, it excludes the condition when both the inputs are 1. In other words, we get a high or a 1 when the inputs are different, which means we get a high or 1 only when one of its inputs is a 1. And when both the inputs are 1, the output is equal to 0. On the other hand, in the case of the OR gate, it is called an inclusive OR gate, since it includes the condition when both the inputs are 1 or when both the inputs are present and output is equal to 1 in this case. The logical expression for XOR operation is given by Y is equal to A bar B plus AB bar, and this is equal to A XOR B. The XOR operation is equivalent to modulo 2 addition. That is, first, the sum is calculated and then the remainder obtained after division by 2 is recorded. Let's try to understand this. These are the two possible input binary combinations for A and B. That is from 0, 0 to 1, 1. In this column A plus B, decimal addition is performed. That is, 0 plus 0 is 0, 0 plus 1 is 1, again 1 plus 0 is 1, and 1 plus 1 is equal to 2. In the next column, that is this, A plus B is divided by 2 and the corresponding quotient and remainders are recorded. When 0 is divided by 2, we get a quotient 0 and remainder 0. When 1 is divided by 2, again we get a quotient 0, but remainder will be 1 in this case. Again we get 0 and 1 for the division of 1 by 2. And finally, when 2 is divided by 2, we get a quotient 1 and remainder 0, since 2 is divisible by 2. Modulo operation is the remainder that we obtained. So in the column A plus B mod 2, we copy the remainders obtained. That is, this column is copied into this column. And we see that these values are nothing but the result of the XOR operation between A and B. Also, the XOR operation can be considered as the bitwise addition without carry. In binary, 0 plus 0 is equal to 0. 0 plus 1 equal to 1. And 1 plus 0 equal to 1. And finally, 1 plus 1 gives 0 with a carry 1. And if this carry is discarded, we get 0. Hence, XOR operation is the bitwise addition without a carry. XOR gate can be used as an inverter. When one of the inputs is 1, the output obtained is the complement of the other input. In this case, when one of the input B is equal to 1, the output Y is the complement of the input A. That is 0 complement, which is equal to 1. Similarly, when A equal to 1, the output Y is the complement of the other input B. That is 0 complement is equal to 1. Consider this XOR gate. One of its input is fed with a 1. So in this case, the output Y will be the complement of the input given to the other input terminal. Hence, Y is given by input complement or input bar. Before considering the next gate, let us have a quick overview of the De Morgan's theorem. According to De Morgan's theorem, x plus y the whole complement is equal to x complement dot y complement. Similarly, x dot y whole complement is equal to x complement plus y complement. What happens is, the complement is applied to each of the term inside the bracket. So it becomes x complement and y complement, and this OR operator is replaced by a AND operator. That is what we get here. Similarly, in this case, complement is applied to each of the variables, that is x complement and y complement, and this AND operator is replaced by the OR operator, and that is what we get, x complement plus y complement, or x complement or y complement. Consider this expression y is equal to a bar b plus ab bar. This is the logical expression of XOR operation in the SOP form. Now we try to get the y complement. That is this entire term complement. That is a bar b plus ab bar, the whole complement. Now here we apply the De Morgan's theorem. And according to that, we apply the complement to each of these terms and replace the OR operator with the AND operator. So we get a bar b the whole complement dot ab bar the whole complement. Again, we apply the De Morgan's theorem to each of these terms in the brackets. Hence we get a complement the whole complement, and this dot is replaced by the OR operator plus b complement. Then dot, applying De Morgan's theorem to this term, you get a complement and b complement the whole complement, and the AND operator is replaced by the OR operator. By Boolean algebra, a complement the whole complement is a plus b complement ANDed with a complement plus b complement the whole complement is b. Now we try to expand these terms in the braces. Hence we get a into a complement plus b complement ANDed with a complement plus b. On expanding these terms, we get a complement plus ab plus b complement a complement plus b bar b. By Boolean algebra, a complement is 0 and b complement b is 0. Hence we get ab plus b complement a complement. And since logical AND operation is commutative, you can write this term b complement a complement as a complement b complement. And hence finally you get y complement as AB plus A complement B complement. And this y complement expression forms the output of another gate known as the XNOR gate, the exclusive NOR gate. The XNOR operation is the complement of the output of the XOR operation. As we have seen previously, the XNOR operation is given by the expression y is equal to A complement B complement plus AB. In the case of XNOR gate, the output is a 1 when both the inputs are equal. Hence, it is called a coincidence gate or an equality detector. Here, when both the inputs are 0, the output is a 1. And when both the inputs are 1, the output is again 1. That is, the output is 1 when both the inputs are same or equal. In the other cases, when the inputs are not equal, we get an output 0. Similar to the XOR gate, the XNOR gate can also be used as an inverter. When one of the inputs is 0, the output is the complement of the other input. That is 0 complement equal to 1. Similarly, in this case, when A is equal to 0, output is the complement of B. That is 1 complement equal to 0. Similarly, when B is equal to 0, the output Y is the complement of input A. Consider this XNOR gate. When one of the inputs is fed with 0, the output Y is the complement of the input applied to the other terminal. And this is how the XNOR gate is realized as an inverter.